This video is part of CAE Associates ANSYS e-learning series. CAE Associates is an engineering consulting firm in Middlebury, Connecticut, specializing in finite element analysis and computational fluid dynamics. We have been an ANSYS channel partner since 1985 and have developed our ANSYS e-learning series to help you maximize your software investment. Please visit our website, which includes an extensive resource library with over 250 items and counting in an easily searchable area. We also invite you to visit our Engineering Advantage blog, where we share insights from our many years of performing engineering analysis. CAE Associates also offers an extensive schedule of ANSYS courses taught at our Middlebury office. If you need help deciding on the best courses to take for your application, visit our CAE University page. The complete library of e-learning recordings is available for viewing in our resource library and also on our YouTube channel at youtube.com/CAEAI.
The topic for today is ANSYS element selection, and what I want to cover is some information in terms of the details of going through the process of deciding which type of elements you're going to use for your particular simulation. And the answer to which elements should I use is it really depends. What is the goal of your analysis? Are you looking for displacements, temperatures? Are you looking for detailed stress results? And these will enter into the decision process of what element is most relevant for your particular application. Also, what are the shapes of my part? Is it a long, slender part? Is my analysis part bulky type solid? So the element type that I select, or the different types of elements you're going to select, are based on not only the geometry, but also on the results. And then the other big factor that enters in is the computational requirement. If my analysis is a linear, elastic, static analysis, I may be able to afford to use a whole lot more elements. I just kind of mesh with all tetrahedron elements, where if I'm running a time history solution that's going to run for hours or days or anything that doesn't run overnight, I'm going to spend a lot more effort getting the most efficient elements and element mesh for the particular problem in case. Now, one of the advantages of ANSYS is you have lots of elements to choose from. If you go back to version 11, there's actually 186 different element types available to you. So pretty large list, and there's some challenges in terms of which element types to select from. All these elements are still in ANSYS. Some of them have been archived and put as legacy elements, but even now at version 14, we have 166 elements available to us. More or a little less elements, but actually new elements have been added, and a few elements have been put into the archives. So with this number of elements to select from, what's the approach that we should use as a user to determine which is the best element type to use for my particular application? What I like to do is go to the ANSYS help. And in the ANSYS help, if you go through the ANSYS mechanical APDL help under the element reference guide, and under that is a summary of different element types. And the nice thing about this is it gives you a pictorial example of all the different element types in ANSYS, whether they be beams, combination elements, fluid elements, solid elements for structural, etc. So you have a choice to look at the different element types, get into more detail. So let's take, for example, the beam 188 element. So if I click on under beam elements, it isolates to the current elements that are available. If I click on beam 188, now a little dry, but if you read through the details here, it gives you an explanation of the application and the details on this particular element type, and some of the options that you can change as a user before you perform your analysis. So if we scroll down through, in particular, one of the things that we often adjust in defining all of the different element types is the so-called key options, where the key options are specific requirements or specific settings that are directly applicable to this particular element type. And one of the key options available for beams, as well as some of the other elements, is a shape function along the length criteria. So if I look at key option number 3 for the beam 188, you notice the default, it says 0 equals linear. Now that's the default actually for ANSYS mechanical APDL, or classic as commonly known. The actual default for the workbench mechanical is quadratic, which is key option 3 equal to 2. But we can adjust that as a user if we want a cubic deformation response to be used as well. So this is one of many settings that you can set, but this is a common application in terms of adjusting things for your particular application that might be relevant. So at this point, what I'm going to do is just to get a feel for the audience in terms of what applications and what different element types they use, we'll open up our first poll. And so there should be a poll that's going to show up, and the poll allows you to answer questions about the which type of elements you commonly use, whether you use all solids, whether bricks, shells, or a combination, just to get an idea of the user base. And when the poll is done, what I'll do is go ahead and provide the results to everybody so you can see, anonymously, of course, the colleagues' response. So it seems like things have stabilized, so I'm going to close the poll and then share the poll results. And so a majority of people in this particular webinar use a solid element. Some use a combination, but a majority are solid elements. So we're just going to call this okay. So moving back to the element types, so we've got many different element types available in ANSYS. The element types we select control which active degrees of freedom that ANSYS will solve for. So whether we're using a beam element, a truss element, a 2D solid, the actual finite element calculations are based on the active degrees of freedom for these element types. So one of the things to be a little careful about when you're running very large models is that if you're using, for instance, a lumped mass element, or if you've got beams and shells, just be aware that they carry extra degrees of freedom. And if you take, for instance, a mass with rotary inertia, you're adding additional degrees of freedom there. And if those aren't necessary, you may want to choose the key option that keeps those elements to just the translational degrees of freedom. For all these different element types, the deformations that ANSYS can actually predict are a function of the shape functions. So what shapes can these elements distort into? And for the bricks, shells, solids, they all allow us to look at both a linear type shape functions or quadratic shape functions. Now, there are some exceptions with some of the 2D elements where there's extra shape functions added for both the quadrilateral 2D and the 8-node bricks, which will account for bending with the additional shape functions. And we'll show how we can access those in the key option settings as we talked about previously with the beam element. We can also use those same options with the solid elements. If we look in general between the different options of using the lower order elements versus the higher order elements, there are a number of functionality improvements that we gain from using higher order elements. One of them is true curved surface representation of our structure. So in general, we can use less elements in the higher order elements than we use for lower order elements. Now, sometimes we prefer to use lower order elements because in terms of stress evaluation, which occurs at the integration points, we have the same number of evaluation points in general with the lower order elements versus the higher order elements. So if that's the important criterion, then maybe I'm going to stay with the lower order elements. And a lot of times we'll use a hybrid mesh where we use the higher order elements on the surfaces where we have, for instance, contact, or we want to model our curvature, and we can transition to the lower order elements away from there as well. In terms of meshing operations, our beam elements in ANSYS mechanical APDA will meshing with line segments. In mechanical, we may be using design modeler to define our cross sections and view those. And for specifying each of these different element types, when we go through the meshing operations, to select a lower order versus higher order element is provided through the advanced settings under mesh controls. So under mesh controls, we can specify whether our element mid-side nodes are kept or whether they're dropped. So let's look a little more detail on beam elements. So why should we use beam elements? The obvious answer is they're easy, they're fast to solve. They follow beam theory. But oftentimes they have advantages if I'm not interested in capturing local stress concentration effects. If my goal is to capture forces and moments, then actually the beam elements gives me a direct path to get those results immediately directly from my analysis. Often also may use beam elements if I'm modeling in detailed 3D solids my local part, but my support structure, where I don't necessarily need detailed results from, but I do want to capture its stiffness correctly, I can transition from my 3D solids to beam elements, and from that more accurately capture the remaining support structure that interacts with the rest of my full assembly. Now, if I'm going to perform that type of operation, one of the things you've got to be careful about is how do I connect my beam to my solids? So when I connect a beam to a solid, the beam has rotational degrees of freedom, where the solid has just translational degrees of freedom. So we need to use some kind of connection scheme to tie those two bodies together. If we don't, we end up with an error such as a rigid body motion where we have rotational degrees motion in the beam that's not connected to the solid. And we'll go over a little later that connection process. If you look at setting up our beams, we have the choices are the beam 188, which is the 2-node beam, and the beam 189, which is the 3-node beam. And these specifications in terms of the meshing controls can be specified in terms of the element mid-side nodes being kept or not used. In that case, we get the lower order element. Well, let's look at a workbench example of how we evaluate, including the, for instance, the cubic function in our beam that doesn't come automatically within the line body. So if we created a line body in Design Modeler, brought it over into mechanical, with the command block, we can adjust the key option to specify that I want this to be a cubic shape function. And you notice there's a couple lines here that I've included as well in this command block. I first said /GoPR, which essentially says, let me have ANSYS echo the information that I'm including in this command block in my solution information folder so I can verify that I did indeed include this key option setting. And then I also set this ET_CON, off that says don't allow ANSYS to automatically adjust the key options. And finally, I just simply specify that under the MAT ID parameter that key option 3 equals 3 that results in the cubic key option setting for this particular example. If I click on the solution information, I can verify this by scrolling through down to where I've specified where ANSYS echoes back up the element type. And you notice that in the element type listing for the Beam 188, it says that the key option number 3, the third field, is set equal to 3. So let's go ahead and go to our next poll. I'm going to open a new poll here. Open this poll number 2. And just get an idea of the majority. If you do use combined meshes, are they beams and shells, shells and solids, beams, shells, and solids, or single element type? And so I'll go ahead and open that poll. So I'll give everybody a few seconds to go ahead and respond to the poll question. And with all of these, there's no real right or wrong answer. We're just trying to get a little feedback, understanding of different types. And also, we're also looking for any feedback at all from these webinars in terms of what you'd like to see in the future or expanded on based on maybe there's some things that perked your interest in some of these. So we have 100% completion, so I'm going to go ahead and close this poll. Polls in a few seconds. And then we'll go ahead and move on while the poll's closing. Go back to my PowerPoint presentation, and you notice that in the I share the results, the majority of people are single element, or some people that use shells and solids. So another things to consider maybe might be including the act of putting beam elements into your model where it makes sense and where it's advantageous. And that's indeed the next slide, is a couple tips in terms of including beams into my solution. One of the things you can include beams, and maybe you have included them and didn't know it, but when you use the mechanical spot weld feature, it actually automatically includes beams in your structure. And the example earlier where I showed the beam and solid model where there was no connectivity between the two, we can go ahead and use a MPC contact where we can connect the contact being the line body, the target being the face of our solid, and this will write constraint equations that will accurately transfer the rotational degrees of freedom from the beam to the translational degrees of freedom of the solid. So moving on from beams, we also have 2D elements we can look at, and 2D elements allow you to get a much faster solution. A lot of axisymmetric problems can be there's no accuracy loss in terms of running a 2D axisymmetric if my loads and geometry and materials are axisymmetric. Much easier to post-process because we can look at the results directly on the face. We don't have to figure out how it's sectioned to cut open, etc. And the mesh is just a simple 2D geometric mesh, but depending on, again, the key options we set, this may represent an axisymmetric structure, it could represent a plane stress structure, or it could represent a plane strain or infinitely thick type structure. One of the options that's not commonly used, but is definitely available for you to use, is what's called generalized plane strain. Now, generalized plane strain differs from plane strain where the strain in the z direction is not 0, but it's held to a constant based on the settings and parameters you've set up with your particular example. So my model could be a section of a curved cylinder. It could be a long body. There are a number of different options. Let's take the long body example. So if I specify a plane strain type simulation and I subject my model to temperature, I will get an infinite stress because I can't get any strain in the z direction. However, if I change and instead insert generalized plane strain and specify a temperature growth, now, because it allows a constant strain in the z direction, I can capture a combined thermal structural analysis by modeling plane strain where I have infinite thickness for my structural loads, but I don't introduce artificial thermal stresses. Moving on to shell elements. So shell elements give us the advantage of modeling with a thin-walled structure where now the elements don't have to satisfy any aspect ratio constraints. Modeling shells is relatively straightforward. One of the things you've got to be careful about with modeling shells is making sure you have consistent normals. So do I have consistent hour normals such that when I put a pressure load, the pressure will act consistently over all faces? Mechanical APDL, for example, when you plot your model with the element types active, it's going to show the inner and outer surfaces with different colors. So you can clearly indicate the region where I need to reverse my normals to get consistent results from the loading perspective, and also helps in the post-processing. In terms of modeling issues, in terms of setting up or using or accessing our shell elements, again, depending on whether we specify to mesh with a kept or dropped mid-side nodes, will determine which element type ANSYS uses. Now, with shells, ANSYS defaults to running with lower order shells, but if you keep the mid-side nodes, you can get higher order shells. You also may want to consider changing the key options in terms of stiffness, and that's an option that we can specify as well in terms of control. If we're using mechanical APDL, we need to actually override that to get the more accurate elements that include incompatible modes rather than the reduced integration or single integration at the center of the shell and then several through the thickness that's the default. Symmetry boundary conditions is another thing that you will need to consider with shell modeling. You want to make sure that not only are you constraining the displacements, but you're also constraining the out-of-plane rotations as well. And we can take an example here. So if I bring a model with shells, when you insert your model with shells, you can specify a symmetry region. The symmetry region here specified on these two surfaces of the shell will actually constrain the in-plane displacement and out-of-plane rotations. And if I also use the graphical expansion beta option, I can actually reflect my model. So when I go to post-processing, I can actually see the effect of my symmetry boundary condition on my shell. The other thing to be important with shells, if you have a pressure load, you want to make sure that you include the large deformation effects, because the membrane response will only be captured if that's defined. Without that effect active, you may get artificially large deformations. Some other tips about shells. Again, you can use the advanced meshing controls to specify lower order versus higher order. So those are shell elements. Then we can move forward to, sometimes we may have a structure where it's a tapered section, or whether we're specifying contact elements, where the shell element makes it much more difficult to define that, but we can use kind of the best of both worlds in terms of keeping large aspect ratios, but using an ability to model tapers, and that's using what's called the solid shell element. So we have a solid shell element 190, then this is accessed through Workbench by the sweep operation. If you use the auto thin solid, it'll actually mesh automatically with these solid shell elements. The solid shell elements, faster to solve than the solid elements, since we can use a lot less of them because we don't have to obey a good aspect ratio through the thickness. The disadvantage of these elements is that you have to be a little careful when you define them. You want to make sure that you mesh with the thin surface operation, or if you're defining them manually, you create a consistent z direction, since the thin direction, where ANSYS will decouple the translational response and the moment response, is only defined correctly if the z element coordinate system is normal to my solid shell elements. So, time for the third poll. So we're going to open up one more poll. I'm going to go ahead and open the poll. And the third one is that, have we piqued any interest, or is there an interest in the future on looking at more details and maybe some training in any of the different element types? Maybe more details on shells, shell modeling, or beams. And so we can address this with either additional webinars or short courses maybe in the future that will cover any of these topics. So I'm going to go ahead and close the poll, since we've got the majority of people have answered, and go ahead and allow you guys to see the results. And it's pretty uniform across the board. So I'm going to go ahead and save these as my poll 3. So solid elements. So solid elements, from a perspective of modeling, one of the advantages is usually a little more straightforward. We're just modeling the specific geometry that we're actually trying to simulate. We can include stress concentration effects. This can be good and bad in that you can include and capture the local stress concentrations if that's the goal of your analysis. But you also have to be careful that if you've created singular type results, so stresses at sharp corners or at fixed constraints, for example, to understand that those results are numerical and aren't necessarily real. If we use the lower order element, we have the option of adding the additional shape functions, and this is the key option number 3. We can set this to 2 for enhanced strain. The default is full integration, or what's called B-bar method, which is generally more applicable to like a metal forming type simulation. So to get a more accurate response in bending, allowing us to use less elements, if we decide to go lower order bricks and save us some computational effort, we can definitely do that. And if we're using Workbench, the nice thing is that if we look at the solution information, we can go in with our solid. We can add key options. In this case, key option 3 is set to 0, so the default is the B-bar formulation. So I can, if I wanted to override this, I can actually go in and simply insert a command block to override the type of element formulation used within the Workbench as well. So if we look at meshing controls, and depending on how we set, when we use the Workbench mesher, it's going to use a hybrid of tetrahedrons and bricks, higher order bricks by default, lower order if we tell it to drop the mid-side nodes. And this slide just shows kind of the transition between the two of these results. There are many other elements available in ANSYS. Contact elements for point-to-point, point-to-surface, surface-to-surface. Unfortunately, we're running out of time since we control these webinars to be 30 minutes. So won't really spend much time just making you aware that there are many different types of contact that may be useful for applications that maybe you're not aware of, such as like a beam-to-beam type contact. As well, there are a number of different specialty elements that can be used. So these specialty elements can be used, for instance, for defining lumped masses, for defining a multi-point constraint, such as sliders between our two parts, and maybe bolt pretend. Some people may have used that one in the past. So that concludes today's webinar. I appreciate you attending. If there is any follow-up questions or anything, I will check the chat line. If they need PE credits, again, make sure you fill out the survey that Christina will send you at the end of this class. So thank you, and have a good rest of the afternoon.